last new content. Last new content for the course. You'll go away next week for Thanksgiving. When you come back, we'll have 1 week after Thanksgiving. I'm just going to sort of do wrap up and be available to answer questions about papers, because you guys, that's what you'll be working on. Okay, so this is it for the new content. This is also the last section of the course. I know I've kind of forgotten to mention, we still have section exercises in the second half of the class, and I also have forgotten to go back and grade a lot of them, so I will be doing that over break, so that way you know kind of where you're at as you finish the paper and go into the final. Okay? Before I get started, any questions about anything at all? Thank you. Nothing? Okay. Our new content for today is, I'm going to briefly summarize the 2 chapters of the textbook that we skip, because I don't think we really need to do it. And then I'm going to finish by talking about ordinary least squares regression, which is a type of analysis that we would do when our independent variable and our dependent variable are both continuous, which means that we can count them, that there's a lot of range to them. Prior to what we've been doing, we've been looking at groups. So with the chi-square, you have 2 nominal groups, or sorry, 2 variables that are nominal or maybe even ordinal. We looked at difference of means and difference of proportions, when you had the independent variable being a group and then a dependent variable being either a count or a percentage. But before I get to ordinary least squares regression, I need to go over correlation, because OLS, in the neatness of what mathematics is, it allows math to be different approaches to get to the same answer. And so the ordinary least squares that I'm going to show you doesn't rely a lot on correlation, but other disciplines do talk about ordinary least squares regression in terms of variance and covariance and correlation. So I'm going to teach you just a little bit about correlation, but not enough to actually do it, because nobody does it anymore. This is like 1960s and 70s statistics. We don't really do it anymore, but it is a concept that we have to know what it is. So correlation is the relationship between 2 variables such that changes in the values of one variable are accompanied by changes in the values of the other variable. The correlation of 2 separate entities such that when one changes, it affects the other one. Here's a good example, a little presidential campaigning. We have 2 candidates, Pete Buttigieg, who has been criticized for the fact that he worked for a private equity firm and made a good fair amount of money doing that. And so we have sort of like this class war going on in the Democratic Party about whether or not it's good to have made money or not. And Kamala Harris came out in response to a tweet, and she said, you know, the amount of money that I've made from private employers. And her answer was $0. I've always worked for the people. So she's always sort of had a government job. Then a friend of mine hops on Twitter and he's like, then why is her net worth $2 to $3 million? And this bothers me, because Jeremy should know better. How would a woman who has worked in public service all of her life accumulate a net worth of $2 to $3 million? No, you can't do that. Can't do that. So how would a adult woman have a net worth of more money than you would expect? Okay, perhaps. Where does a... Man, maybe this wasn't as obvious as I thought it was. Maybe Jeremy isn't that stupid. Right? is there anybody else that could help her build her net worth? Her spouse. Okay? So she said, I've always worked for public institutions. But if her household has a net worth of $2 to $3 million, which she has to report because it's part of her household, why are we assuming that that's all her money? Couldn't it have been his money? Right? Don't you sort of have joint assets when you get married, particularly in the state of California, which is a 50-50 kind of state? Right? So the idea that somebody's net worth could be influenced by a partner, a legal partner. And that just completely went over lots of people's heads. The example that I like to use to explain correlation is the hand thing. Did I do the hand thing in here? I did? So there is a correlation between my right hand and my left hand. I am right-handed, even though I wear my watch on my right hand. It's because why would I look at the time on my non-dominant hand? This is the one that's doing everything. So if I move my right hand when it's clasping my left hand, there is a correlation between the two. And this is kind of perfect correlation if it's my hand that's doing the moving. Okay. There is a relationship between the two variables. When we describe relationships between variables, this should be a little bit of review. I think we did a little bit of this in the beginning. But let's look at the idea of how that relationship exists. Now, this figure up here, this is known as a scatter plot. So we have our x variable, our independent variable. We have a y variable, our dependent variable. We name them x and y because of the axes. And each of these dots represents a single data point, or a single observation, and the value of the two variables for that observation. So let's say that's you. That's you, Mallory, right there. There you are. I don't know what x and y are, but that's you. Okay. And I'm over here. That's me. The dots is known as a scatter plot. Why? Because the dots look scattered. And they do that because it's a continuous variable. There is some sort of difference in the x and y. You end up with kind of like a cloud, a little cloud of dots here. And what we're going to learn today is how to best summarize that cloud of dots. And what I'm going to teach you is how to draw that magic line that goes through the cloud of dots to represent the relationship between x and y. Here we're making an assumption that the relationship between x and y is linear, which means a line. But if you were to look at this cloud, in example B, this is the example of a nonlinear relationship. The effect of x on y changes as the value of x increases. Has anybody here ever heard of something in economics called the Laffer curve? So I won't. Don't call on you is what you're saying. You acknowledge that it exists, but please do not call on me. Okay. Nobody? The Laffer curve was most popular in the 1980s. An economist by the name of Arthur Laffer somehow got this in front of the folks in the Reagan administration. And the idea behind the Laffer curve is there's a certain point where when tax rates, variable x, as tax rates increase, the incentive to earn more money decreases. And so this would be your income, all right? And so at some point, we're like, yeah, it's worth it, it's worth it, it's worth it. But at some point, the tax rate gets so high that you don't care to earn that extra income. In the I want to say 30s, 40s, maybe even to the 50s, the top tax rate in the United States was 90%. But it was like your third $1 million. So you were taxed at a lower rate up until like $3 million. And then when you hit $3 million, every dollar over $3 million was taxed at 90%. So if you earned a fourth million, you actually only took home 100,000. And at some point, people go, you know what? It's not worth $100,000 to work for $1 million. Or, you know what I meant? Okay, it's not worth that work. So just go ahead, and I'll just stop it, to $3 million. That's the argument behind this nonlinear Laffer curve, that at some point taxes become a disincentive to earn more money beyond, like right here. As if we've ever seen anybody go, no, that's good, I make enough money. No, I'm fine right where I'm at. I wouldn't have to, receive less of more. Just an idea. When we're also looking at these scatter plots, these clouds, the clouds have directions. They're either positively associated, so that when X increases, Y also increases. So when your husband or your spouse earns more money, your household has more money. That's the way that works. Or as X increases, variable Y decreases. As the price of gas increases, sales of SUVs and other large fuel-inefficient vehicles decrease. Essentially, if you're a car manufacturer, you have to predict gas prices because it takes so long to ramp up sales. So when gas was $4 a gallon, what kind of cars did people buy? Small cars, hybrid cars, electric cars. Now that gas is $2 a gallon, I get 14 miles per gallon. It's okay. It's not that much of a cost. And what don't people buy? Little tiny cars. So car manufacturers, they have to sort of guess what the consumers are going to want based off of gas prices. This is where correlation comes in. So now that I've got you understanding what a scatter plot is and how as X changes, Y changes, here we have 4 scatter plots. And starting from A to D, we'll see that the influence of X on Y changes. In this first example, it actually has the dots appear to form a line. That is known as perfect correlation. Perfect correlation is when you transform one number into another one, Celsius to Fahrenheit. That will be the same every time. Currency exchanges should be. So as you change dollars to euros, if you exchange 5 euros for $4, she should exchange 5 euros for $4. And there's actually a field of economics where people try to find when the exchange rates aren't perfectly correlated. It's known as arbitrage. And you just trade currencies so that you can get the difference when there isn't perfect correlation. B, we can see that as X increases, Y increases also, but there's more, and this is the technical statistical term, noise. There's more variation. You know that one, variation. There's more variation in the differences in what corresponds to that value. So if we look at this spot here with variable X, at this point in X, there's actually 3 different corresponding Y values. Oh, I lost it. I think it was this one, and this one. As the correlation between X and Y gets weaker, the cloud expands. So we go from a line to an oval to a circle. It's hard to say what line you could draw through this last one. Is this one the representation? Is it this one? Is it that one? Hell, could we get really weird and go straight up and down? I don't even know how to describe that relationship. What we're seeing here is that the correlation, the amount at which they move together, is decreasing. Correlation, when you're reading an article, is represented by the statistic R. Nothing Greek, just an R. One of the assumptions behind correlation, first of all, is it's measuring the amount of a linear relationship. Again, no curves, no shifts in influence, just a straight, linear, either positive or negative relationship. The sign of the correlation indicates the relationship. So if it's positive, as X increases, Y also increases. If it's negative, as X increases, Y decreases, goes down. And we can represent the amount of correlation as a number between 0 and 1, but because we have two directions, it's actually -1 to +1. The value of 1 indicates perfect correlation. So the idea that the clasped hands move together completely together. They're clasped, they're right next to each other. And we are saying that the relationship between X and Y is because of the movement of X. So the fact that my left hand moves because my dominant right hand moves it indicates that there's perfect correlation. The degree to which they move together depends upon the nature of the relationship. So how could I weaken the correlation between X and Y? How could I weaken the correlation between my right hand and my left hand? Anybody? How can I weaken this correlation? I can separate them, right? So now they're separate. Now, if I say that X and Y have 0 correlation, that means, for example, I can move X and it has no effect on Y. Or conversely, I could move Y and it is independent of the movement by X. What if I had weak correlation? What is a situation in which my unclasped hands, I can make my right hand move my left hand? Well, that's twisting at my waist. That's my core. I'm moving them both at the same time though, right? Is the movement because of X? So we're observing X and Y move together. Right? They both took 2 feet to the right. And they both moved 2 feet to the right, even though there was another reason why. Let's call my feet Z. That's an exogenous variable, Z. Z caused both X and Y, but it made it appear that X and Y moved together. And unless you know to look for Z, you might have an issue. Right? Maybe I could be on like an American Ninja Warrior course, and I got to do that thing with the pegs, right? So my right hand would cause movement in my left hand because my right hand pulls my body up. Okay. So correlation is this weird thing. We can find evidence for it, like in a cloud. But the linkage between the two is based upon our assumptions. So So an expression in statistics that you should have heard is the idea that correlation does not denote causation. Correlation is not causation. When we calculate the amount of correlation, we can try to, take this quantification and give meaning to it. So something is strong if more than half of the movement is because of another variable. Again, this is chapters 11 and 12 in the textbook that I skipped. It's there. One of the other things that if you were to take a look at it, you'll notice is that there's actually, to calculate the amount of correlation, you have to look at how variables covary and vary together. So variance, we've dealt with before from chapter 4. Variance is the difference in the scores for each variable. And that just shows how they vary. Covariance is the idea that two variables can, because they're correlated, share variance and move together. And this is the best example I've ever seen to help explain the difference between variance and covariance. Height and weight have variance. So if I measured each of you and how tall you are, and I measured your weight, they both vary. And we will get differences amongst us. Some of us are taller, some of us are shorter, some of us are thinner and wider, just like the variance of a curve. But the relationship between height and weight is related. The taller you are, the more you weigh. When a child is born, one of the first things we do is measure their height and weight. They are 20-something inches long. We don't even call it high, we call it long because they can't stand up yet. And they weigh about 8 to 9 pounds. So if you stayed 20 inches, your weight is kind of limited. But as you get taller, there's more room for the variance in your body. So that's why with children we track their height and their weight, not just their weight. Because no matter what happens, as you get older, you also get taller, you will weigh more. That's covariance. The degree to which, because you are taller, you can weigh more. Some people do linear ordinary least squares regression from a perspective of correlation. Psychology and sociology are the ones that I would sort of point to and say, if you're in one of these classes, you'll see regression as expressing the amount of variance and covariance. There's a procedure known as ANOVA, A-N-O-V-A, and it's an acronym for analysis of variance. So you might see an ANOVA table. And all the ANOVA is going to do is give you this measure of correlation, and the Pearsons are, and probably a measure of how much of the correlation or of the variation is explained because of the correlation. That is a way to do linear regression. I learned it in a slightly different way. The way that I learned it harkened back to math from 6th grade. Aw, you're cute. Can I borrow this? Remember in 6th grade you'd walk in and in math you'd get graph paper? And you were like, oh, graph paper, it's so awesome. I wonder where they get it from. Thank you. And you know that day was going to be really easy. Because the great thing about doing graphs and math is that all you got to do when you have your gridded graph paper, whatever question it is, you draw yourself an axis. I don't know if one of your teachers was like mine, but they always insisted that you put the little arrows on. My daughter got dinged on her homework for not putting the arrows on. I was like, oh, Abby, no, you have to do that. Yep. And then you get a set of coordinates, right? You get a set of numbers. You're smiling. You're like, I remember 6th grade. And this is easy. The first one is X. This one is Y. So you go over 1, and you go up 2, and you put a dot. Man, this was the easiest math. It was just like plotting and drawing little pictures. Right? You'd get a series of coordinates. I remember exercises where they'd give you like 20 coordinates and you plot them all, and then you have to like connect the dots and see what the picture drew. Hey, good math, right? That was like esteem building math. It's not actually math, by the way, but so you'd be given a series of coordinates, and then you were told to draw a line. Like this is A, this is B, this is C. And then you had to calculate the slope of that line. And the slope of the line is the difference between your Y's and the difference between your X's, right? Delta Y over delta X, rise over run. Maybe I have that reversed. Anyways, okay. And you had this equation. Y equals mx plus b, where m is the slope of the line and b is the y-intercept, where you cross the y-axis. Right? Everybody got good thoughts flashing back to 6th or 7th grade. You all did this. Right? You'd have to draw things like, plot the coordinates for a parallelogram. Well, here's why I think that was probably the most useful math that I ever learned in high school to get me to the part where I'm teaching as a statistics professor now. Let's play a game. And if I'm playing a math game, I'm probably cheating. Or I know I'm trying to get one over on you. Let's play a guessing game. I will give you absolutely no information at all, and I would like you to guess the age of a person. Now, you have math training. There is an answer that is the best answer that will earn you a shiny gold star. What's that answer? What is the best guess at the age of a person? High fives if you get it right. Maybe a fist bump. Depends. Although the amount of time that it's taking to answer this question, you're losing your fist bump. Right now you're just going to get a good job. What is the best guess when confronted with this question? Guess the age of a person. Fuck it. I'll give you the high five. The answer is, the best guess to the answer to this question is the mean, mu. The best answer to this question is not actually a number, it's the mean. Why is it the mean? Why is the mean the best guess as to what the age of a person is? It is the average. Think back to our curve. The mean is what? In a normal distribution, the mean is also two other measures of central tendency. That was a hint. The mean is also the... Somebody? I heard it. It's the median, the mean, the median, and most importantly, the mode. Because the mode is what? The most frequent answer. So the best guess in a guessing game is the most frequent answer. With absolutely no information of who the person was, the best guess for you would have been not a number, but a statistic, the mean. And the guess, if you say the mean, according to the CIA fact book and whatever year I originally wrote this slide, the average age of a person in the world was 38 and a half years old. Okay? That's wrong. That's not the age of the person I'm thinking of. Close. So that was a guess with no information. That was just a guess of the dependent variable y with no information at all. I will give you one piece of information, a x variable, so to speak, so that you can predict y. And I will actually tell you who y is. Y is my wife. So think about it for a second. I will let you ask me one question to have a better guess than the average. You have to pick something that you think would be highly correlated with y. So you have to pick an independent variable that is highly correlated with my wife's age. You may not ask sneaky questions such as, what year she was born, because I'm not that dumb. Nor may you ask what year she graduated high school, because that's just y minus 18. So, what question would help you understand my wife's age? Okay, that's a pretty big gap though, right? So basically you want to know if my wife is above 70 or below 70. Yeah, you do you. I'm going to keep my money on him. What do you guys think? One question, one piece of information to help you understand my wife's age. Who said that? Did you say that? Who said that? Because I got another high five coming. Did you say that? Yeah, you did. I know you did. Why? Why do you want my age? I'm talking to him, not you. I'm talking to him. Why?
Probably be roughly the same as your wife.
Why do you think that? Okay, because you have observed people who are married, yes? You know people who are married to each other? Yeah, right? So you've met them. You know they usually are within some years of age together. Okay? What year is it? It's 2019. I'm 41 years old. Okay? So I've given you the x variable, 41. How old's my wife? Okay, we got 39. Anybody else? $40. Okay. Any other guesses? 41, 43. You guys stink. She's 42. So 40, my husband, that's me, 40, 41, and there we go. Where'd that dot? So this is a graph that I took from the internet many years ago. I do not know if it is accurate or not, but let's just pretend it is. The x variable here is the husband's age. The y variable is predicting the wife's age. What would we say about the relationship between husband's age and wife's age? Using some of the terms that we use to talk about correlation. What's that look like? What kind of relationship are we seeing? Linear relationship. Why is it a linear relationship? Okay, so it appears that we could draw a pretty good line through this scatter plot to describe the relationship. And if we draw a straight line, that good? Assuming it's actually straight? Okay. Draw a straight line through it. That looks pretty good, right? What direction is this line? Positive. So as x increases, y also increases. As men get older, their wives get older. Assuming it's the same wife. My dad had 3. I think they got younger each time. Dad kept getting older. They stayed the same age. Bonus points if you get that reference. Yeah, a girl. All right. So it's positive and it's linear. Tell me something about the extent of the correlation. Is the correlation strong or weak? Why is it strong? Yeah, because the cloud is right there at the line. What would a weak correlation look like? It'd be a giant circle, right? We'd have 30-year-olds marrying 80-year-olds, and vice versa. Okay? Brief history about ordinary least squares regression and where it came from. The first published paper using this method was about the orbit of comets, done in 1805. So 214 years ago, a man, it was a him, without a computer or really big telescopes, were charting the paths of comets in the sky to try to predict them by hand, without a computer and electricity. Legendre publishes a paper in 1805. People look at his method and they're like, this is pretty cool. You're helping to quantify the amount of variation, or let's say correlation, between two things. We like this. A German mathematician by the name of Gauss says, oh, I did this. Yeah, it's okay. I didn't really think it was that important, though. I did this a while ago. We knew this already, didn't we? Tries to claim credit for ordinary least squares. He points to an unpublished paper that he has, and he's like, here, look, you can see here where I do some of the same things. And everybody's like, yeah, nice try. The thing about Gauss, though, is he was like famous. He was already he was already a well-known mathematician. He didn't need to claim credit for this one. Legendre wins because he had named it the method of least squares. Ordinary least squares regression is what we call it today, OLS. The least squares. Where does this come from? Let me show you some of the math. Again, I'm not actually going to ask you to do any of this by hand. Clearly you can, because in 1805, the French guy did it about comets. So in 2019, I'm pretty sure you guys could take, a 2-variable 10 observation study and go through and do this by hand. You'll hate me, but you could do it. What we're doing, very similar to y equals mx plus b, is we're guessing at what our y variable will be as a function of, okay, the first one is beta 0. Beta 0, is sometimes called something else. Alpha. We have a problem. We've already named like 3 other things alpha. So I'm going to stop calling it alpha. We're going to call it beta 0. And beta 0 is the y-intercept. Why would I put a 0 there? Because the y-intercept is where the line goes through the y-axis when x equals 0. That was what our y-intercept was. What value of x gives us a y of 0? That's the y-intercept. It's also referred to as the constant, because no matter what the value of x is, the constant, you are going to start at that number. Beta 1, that was our old b. Beta 1 is our old m. Of the mx plus b. Beta 1 is the first coefficient that we generate from our first independent variable. That's why x has a 1 on it. This setup would allow us to do multiple independent variables. With ordinary least squares regression, you can have more than one independent variable. And I'll show you how that works when we get to working through an example. This class is an introductory stats class. We haven't really encountered that before. So a chi-square contingency table is between one independent variable and one dependent variable. A difference of means test, one independent variable, one dependent variable. That's intro stats. It's hard to describe how something happens with just one factor. So ordinary least squares regression allows us to build in more explanatory variables, more independent variables. x1 is still x. This is new, plus epsilon. Squiggly e. Epsilon is what we call the residuals. It's also the errors that happen. The errors are generated when the line is wrong. So the data point for that person was underneath the line. There's a difference between what we observed and what we predicted. That's known as a residual. That distance is still left to explain. Why that? Ideally, all of these errors are going to cancel out. So all of these observed differences from our predicted value, we think they should all cancel out. We think that this should just be noise. This should be something that happens because we're stochastic. There's a randomness to what human beings do. Right? There's a gap here between the line and my wife and I. There must be an explanation as to why I married a woman that is 14 months older than I am. So depending upon what month it is, sometimes she's 2 years older than I am. I wonder how that happened. I have an explanation. I skipped my senior year of high school. So I was a freshman in college at 17. She was a freshman in college at 18. We met on the first day of classes. That explains the year difference. That's the randomness of us. The fact that I had skipped a year of high school. That's not going to be captured in any model out there. Okay? That's the noise. The fact that I chose to do something unrelated ended up causing a 1 year, 2 year, 14-month difference between our ages. When you were doing the lines in math, you didn't have any errors, right? You just had 4 dots and you connect the 4 dots. And so you didn't need that. And so the errors were assumed to be 0. And in fact, we hope that they will cancel out. Okay. So that's what the equation looks like. But you still know that you have to generate the slope. That's the whole thing you had to learn in 6th grade was where the hell does the beta come from? Because you have this, we'll back into this once we know where the line is, but this is what you need to find first. You need to find the slope. Want to show you a couple more things. This is y hat. Yes, that's what we call it. Put a little caret over the y. That's the predicted value of y. So that's the coordinate on the line. The line is the y hat. You would get y hat by having your value of y plus whatever noise there is in there. So that's another way. Or you do this equation, and you notice we leave the errors out because we assume that they're 0. So that equation should equal that equation. Y bar, we know what the bar means. The bar is the average. But now we're going to put the bar over our y, and that's just the mean value of our y. Beta is our new version of a correlation coefficient. But instead of explaining the amount of correlation, beta explains the effect of the correlation. Beta is the amount that y increases, or changes, I guess would be better, as x increases by 1 unit. The sign of the beta indicates the direction of the slope of the prediction line. So if beta is negative, beta is the amount that y decreases as x increases by 1. If beta is positive, then y increases as x increases. I had to include this last note on this slide. It works best when y is a continuous variable. Ordinary least squares of regression is an equation that will do whatever you ask of it, even if what you ask is inappropriate and is not what this was designed to do. OLS is like a hammer. And no matter what the object is in front of you, a hammer does one thing. Smash. Just like Hulk. Huh? You could, but not all hammers have pulls. So when I moved this summer, one of the things that I can't find is my hammer, but what I did find was a sledgehammer. And so here I am banging nails in with a handheld sledgehammer. There's no pull on that one. No. right? I also found a tin shaping hammer that's flat on one side and a ball on the other. Yeah. That, coincidentally, is, well, never mind. That goes a little dark there. Not going to go there. So not all hammers can pull nails, but all hammers can smash, right? They're like the Hulk smash. So we could give OLS data that makes no sense in this framework. We could give it an independent variable that is binary, like gender, and we could even give it a nominal variable over here. Catholic, Jewish, Baptist, where the numbers solely represent whatever the hell we decided to give it to, right? Catholics are 3s. And as long as it has numbers, actually that's wrong, you idiot. Our independent variable is only going to be 0s and 1s. Our dependent variable is really only going to be at these 3 spots. I got 3 categories for a dependent variable and 2 categories for an independent variable. I'm only going to have 6 spots where these dots are going to show up, right? I put a little jitter here. That's the technical term for when you make the dots next to each other when they should be on top of each other so that you can show the number of dots. Well, if I tell OLS, find me the magic line, it's going to be like, oh, okay. No matter what data you give it, if you have x coordinates and y coordinates, it's like, okay, I'll draw a line. Smash. There you go. It makes no sense. As you go from male to female, you are less likely to be Baptist and more likely to be Catholic. What? That makes no sense. It will do whatever you ask it to do. Some methods that when you ask it to do something it's not designed to do, like the computer will just be like, no, not going to happen. When I was dissertating, I asked the computer to do a multi-level model where I was predicting your entrance into a group, and then once you were in the group, predicting the outcome. And I would type it up, and I would hit enter, and then I would go home. And then I would come back the next day after the computer ran for like 20 hours, worked short days then, look at it, and it would still be running. And then I go, and I come back, and 2 days later, it would still be running. So I did something wrong. And the computer is like, well, I'll look for it. And then on the 3rd day, I'd come back into work, and I'd look at it, and I had a red error message. Model failed to converge. That computer worked really hard for 3 days trying to get the nonsense that I told it to do to work, but it's just like, no, there's no way we can do this. If I take nonsense and I put it in OLS, hit enter, I get results. Every time. Computer doesn't even think about it. It's just like, here you go. Not a problem. Oh, cloud of dots. I know how to draw a line. Here's your line. Don't write this down. I just want to walk you through it. This is a single independent variable way to do ordinary least squares regression. Beta 1 is that first B. To do this, you need to know how to do the following things. We see summation signs, which means you're going to have a line in your notebook for every observation. So if you have 10 observations, you've got 10 lines that you're going to be working across, 10 rows. If you've got 64,000 observations, you've got 64,000 rows that you're going across. first thing you're going to do is subtract your value of x. xi, the I represents what number observation it is. So it's the first observation, it's x1, right? Minus x bar, so the mean of all the x's. So you're going to find the difference between x and x bar. You're also going to find the difference between y and y bar. You're going to take those two numbers, you're going to multiply them together, so there's column 3. And then when you've done that for all your variables, you're going to take the total of that column 3, and that's your numerator. Your denominator is the difference between x and x bar squared. We remember why we square things, right? We square things so that when we add them up, we don't get what number? Because squaring things removes negatives, and by squaring something, we'll never end up with the sum of 0. Because it would be bad if we had a 0 in the denominator, right? Again, that's Abby's 4th grade math, where she's working on undefined fractions. 0 in the denominator is really bad. That's why we squared it. There's the term squares. Ordinary, least, squares. So we're going to add all those up, get that column, we'll do the division, and that will be our rise over run. That will be our slope. Once we have beta 1, we can plug that into the second equation. We can take beta 1, multiply it by x1, or sorry, x bar of that variable. So whatever that x bar that we used up there, that's just lazy notation. Sorry. So we're going to do a multiplication. We're going to insert this y bar. It's the same y bar from up here. Then we'll do the subtraction, and that'll be our beta 0, our constant, also known as alpha, the y-intercept. I did this for a one variable, so one independent variable. I want to say there were 8 observations, and it took me 3 pages in my notebook to get all of this stuff. It took a while to do it by hand. Mathematicians would have laboratories in the days before computers, and they would employ people to do the hand calculations on really big sheets of paper. Remember, no calculators, no electricity. Very frequently in mathematics, there was a gender divide. So the men were the ones that came up with the equations, and the women were the ones that did all the work in the lab. Sort of like a hidden figures kind of thing. What we're doing here with ordinary least squares, and this is why we have the least part of it. So when we predict y, we're starting with the assumption that the best prediction is y bar. But once we introduce x, and we then can generate a magical regression line, what we're doing is reducing the amount of errors such that, so let's start up here of yi. This is our data point. If we were to guess the average, the residual would be this whole height, that whole distance there. That's the total amount of variance from here to here, right? From this point to this point. This is the total variance. Because I gave you that independent variable, we were able to draw this magical regression line, and we reduced the amount of error by this much, right? Because we've moved from this point up to this point as our new predicted value of y. that still leaves a residual. And this is actually that epsilon here. This is the residual that we would have. Right there. But we've improved upon the overall amount of variance. Right? So we have this much explained by x and this much left unexplained. The least comes from the fact that this line, the magic line, gives us the least amount of unexplained variance of all of the infinite number of lines that you could draw through the cloud. And that's why it's the magic line. It is the one line that explains the most and leaves the least amount of unexplained variance. Ordinary, least, and then we have to measure the residuals in terms of squares because we believe they cancel each other out and be 0, and 0 in denominators is really, really bad. Ordinary, least, squares. That's where the term comes from. And that's why the line is a magical line. You have a cloud of data, and you are finding the one completely linear line that goes through this cloud of data and minimizes the incorrect guesses. Now I have to make one note. Again, I'm not going to claim credit for this graph because they did it wrong. It should have went from 0 to 0. Like 0 should always be your starting point in graphs. I'm not sure why this data only starts with people that get married at 32 years old. Because I know that some people are getting married younger than that. It might be fake data, I don't know. It's pretty cloud though. Yay for autosave. All right. On the SDA website, if you find two variables that are continuous variables, you might need to do some recoding because I don't like exactly how they measure things all the time. You can run a regression using this website. You can also download the data and run a regression in Excel. Excel does statistics. I don't like it, but they do it. And there are tons of links on the internet. I think I might have grabbed one and put it in Moodle, sort of a tutorial on how to do regression using Excel. I got to remember to turn the weights off. I don't know what that is. Let's run it and see what happens. So I picked out on Tuesday's class two variables that looked kind of continuous. I wanted to reinforce the idea that education has an influence on your income. My wife is a high school, they don't call them guidance counselor, she's a high school counselor, and she likes to explain to her students the value of a college degree. And that over your lifetime, you will earn $1 million more with a college degree than you would with a high school diploma. Something like that. Well, let's test that. So there's two variables in the General Social Survey that are kind of continuous. One is education as measured by the highest year of school completed, from 0 to 20. That's what it ranges. And then they have a dependent variable, the family income in constant dollars. Because this data set goes across time, the value of money changes over time. It's called inflation or deflation if the value of money becomes... Anyways. Inflation is the trope that, well, this is what I paid for this when I was a kid. So, you know, grandma paid a nickel to do something that you now pay $7.95 for. The value of money changes over time. So if you're using data that involves time, we have to have what we call constant dollars. Constant dollars picks a year and makes all of the other years converted to that year's dollar. It's the same conversion that we would do from American dollars to Canadian dollars to Jamaican dollars. Usually $1 American dollar to 125 Jamaican dollars. It's pretty cool to go to the ATM and withdraw like $200,000 and have like 80 bucks. Okay, so that's what a real dollar or a constant dollar is. That's why it's called real income. What does this show? Well, it took the data, it ran the equation, all right, so it got its hammer out, and it pounded out this beta coefficient. Beta, actually we want this one, not that one, this beta, which shows us that with every increasing year of education, you get a positive $3,457. So an extra year of school gets you an extra income of $3,500. Stay in school. That's a test statistic. Go back to this. Oh, no, not that one. Up until this point, we've generated a test statistic, identified a critical value, and then rejected the null hypothesis. With ordinary least squares, this is what we're doing. Here's our data cloud. The null hypothesis says what in regards to the relationship between the independent and dependent variables? That there's what? The null hypothesis says what about the relationship between x and y? There's no relationship, okay? What line makes it look like there's no relationship between x and y? A flat line. If the slope of the regression line that minimizes all of the errors is 0, then we're saying that that as we have a 1 unit increase in x, we have a 0 unit increase in y. Come on, guys, flip the switch. Let the light bulb go off. Okay? Our null hypothesis is that there's no relationship between the variables, which would mean that slope line should be 0. Our alternative hypothesis says that there is a slope, that there is some change in y because of x. Our test statistic is 3,457. That's the beta, beta 1. What is the probability that we would observe in this data a magical slope line of $3,500 when the null hypothesis is, if the null hypothesis were true, scatter dots everywhere, that slope line should be 0. Really, really low. Really, really low. How do we calculate this? The exact same way that we've been calculating it all semester. The test statistic divided by a measure of standard error. And again, we've reached the point where the things that we're doing, we no longer need to be doing by math or by hand. I can do the math to show you how to calculate a standard error. That was 3 more pages in that homework assignment that I tried to calculate 1 beta in. Here's our test statistic. Here's our measure of standard error. Here's our probability. They even do a t-test for us. Okay? So we're still using with ordinary least squares the null hypothesis and alternative hypothesis framework. It's right there. You'd have to do some other stuff, like if you do OLS, I think it's really cool to download the data, get the cloud, see what the cloud looks like, get the line to go through it. It's pretty cool. But I'm out of time, and I guess they're beating down the doors, so.